quick comments. One's an apology for my casual dress. My wife and I discussed so much what's going to be the temperature in Reykjavik in November. Forgot to pack my suit. The other announcement is I have to catch a flight out as soon as this is over. So if you have some interest and you want more information or whatever, I'm happy to do what I can. You may need to check my email address or something like that, and I apologize for that. Yeah, anyway, I am an electrical engineer. I'm an enabler of sorts for the work that you're trying to do. I don't direct the science. I try to make it feasible, to make it the measurements. And so what we have here is a bit of an overview on the technology, where things are going from an electronics point of view. I've also done quite a bit of fiber optic work. I don't have time to talk about that here. So fiber optics are not off the table. So let me start with something we have here called high temperature SOI. This is technology being developed for the aircraft industry. It is a huge market in the aircraft industry, billions of dollars, literally billions of dollars. It will happen. All the engine people are working on systems now. I can explain. That's an interesting topic. We don't have time. You're just going to have to trust me. Now, the aircraft people want electronics rated to at least 225 degrees C and operational for 5 years. But it also means that it has to be within specifications. So a failure is to fall out of specification, not just not work anymore. So the opportunity for working in a geothermal environment is, of course, maybe twice as long. So anyway, it's 225 degrees C, 5 years. Now, if you're going to have high reliability electronics, you better have your electronics able to operate at higher temperatures than that. It can't be so borderline. So in this particular case, and this particular device was developed for geothermal, for the drilling industry, because the aircraft is a control system problem. How do I control my aircraft engine? Not a scientific measurement system, okay? So we needed something a little more high resolution. So the benefit of this particular device, and I played a part in this, has 18-bit dynamic range, which is clearly into the scientific realm of measurements. We took this device and we ran it up to, it quit operating, which was, I think it was actually, I said inside the lab, was right at 375 degrees Celsius. That's really quite hot. Here's its rated temperature operation. Now, before you get too excited, this is one device. If we were going to build an instrument, the entire instrument is not going to have this resolution, okay? So I'll give you an example in a few minutes. Let's see here. This was performed at San Diego National Labs, and this particular part is built by Honeywell. And this is an instrumentation amplifier, and instrumentation amplifiers are good for making downhole measurements, and in particular, I want to suggest thermocouple measurements, along with strain, pressure, things like that. So let me take you back a little bit to when we first started this. It takes a long time to develop new things for aircraft. It's basically a 14-year test prove-in. So you got to develop it first, then you got to spend 7 to 14 years proving it works. And why is that important? Because we all fly in airplanes, okay? So there's a very conservative design in the aircraft industry. They do not plan on making a change tomorrow. They haven't thought about for a long time. All right, so anyway, so we took some of these aircraft stuff, some of the early stuff, and we managed to put it in a well back in 2002, 2004. And we set it up. It fed the data directly to the internet, because I wanted to have people see what we were doing, and my expectation was that after a few months it would fail. It ran for 2 years, and in fact it never failed. The reason why it's no longer running in the well is that we wanted to take it out and look at it, and the operator broke the cable, ting, 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 down to the bottom of the well. It wasn't terribly hot, because we're trying to take baby steps, 193 degrees Celsius or so. This line here is the pressure, it's pressure temperature. What appears to be noisy, and I point this out because I've heard people in the oh, it's so noisy. Well, that's the tide of the moon going around the Earth, because this is months, days. This is days, right? That was basically our first year. The second year it was just pretty flat and boring. Here's another example. This was 2 tools put into 2 different wells for as a test. This was a year or 2 later, and this is a steam flood well where you pump steam in, you heat the well up, and then you turn it off, and you pump oil out. So it's called huff and puff. Anyway, this is surface data along with our tool data. What was beauty about this test is we're getting temperature cycles due to the huff and puff. And temperature cycles are actually quite dangerous to electronic equipment. Anyway, both tools ran for a year. We pulled them out. We still have them. Now, I took some of this electronics, and we want to be able to stay in the well for a very long time. So we need to not have drift, because if you have drift in your measurements, you're going to think things are happening in your reservoir, which are not happening. Okay? So working on trying to make sure we didn't have drift. Inadvertently, to our surprise, when we went and calibrated the tool, our process took out temperature variation also. So basically, this is a room temperature calibration and a 280 degree C calibration, which is, we would promise our equipment it's up to 275 degrees Celsius. And again, I need to remind you, this is not in a flask. This is just the electronics working at ambient temperatures. There's no heat shielding, there's no cooling. There's no cooling on the aircraft engine. All right, anyway, so that was really good. We really had it. Pressure temperature. One of the other issues we have in geothermal as an industry is things are expensive. And so even the surface equipment, in fact, we've done a number of deployments. We've never had a high temperature tool fail. The electronics have never failed in a well. Other than one where a seal wasn't properly cleaned and we developed a leak into the tool. But that's our only failure mode. But on the surface equipment, we had quite a few failures. Anyway, I was trying to make things cheaper, so on my own initiative, I bypassed our normal people, and I took a little Arduino here, if you know what those things are. They cost about $10 to $50 US. Hooked it up to a little interface thing here. This is one of our tools right here. This is the actual high temperature tool board. It's a little out of focus here. I didn't take this picture because I never thought I was going to show a presentation. I took this picture for my benefit. This represents our cable. There's about 3 kilometers of very fine wire. It's probably a very bad case. Anyway, at one point with this in the oven, here's our pressure readings held at a fixed value. And it's actually pretty good performance. You can see this here. And the reason why I use pressure is because that has the largest gain of the instrumentation amplifier. It's about a gain of about 300, and temperature is only a gain of 7. So our amplifier gain is the most, so our noise is going to be the most here. And this is 2 different modes of communication. I won't go into that. But it's pretty good. So that's sort of the past. I gotta pay for my visit. I fell in love with this little thing and doing some stuff. So I actually wrote a book on Arduino projects for scientific measurement. And what was interesting when I was here at university, a drilling professor at the University of Reykjavik, I mentioned this to him, and he said, oh yes, well, all his students know how to use it, and so does he. And they've already been doing some projects in drilling with this thing. And I said, oh my gosh, yeah. So I think this is the future, that Icelandic students, at least in the short term, are going to graduate not just knowing geothermal, not just knowing their discipline of drilling or reservoir engineering or ever such, but they will understand actually how to make scientific measurements using electronic devices. And the same thing applies to fiber optics, same principle. Okay, so where are we going in the future? We'll try to cover this real quick. There's a couple things I think are pretty exciting. Again, I spend a lot of time with the aircraft people. This is the newest thing for the aircraft. This is a 32-bit. The prototypes that they actually sent me ran over 300 degrees Celsius. I understand this one may not quite get there, but it's 32-bit. This is a complete circuit board, memory, clock oscillators, everything we need is in this little square, and it's only less than 0.9 inches and 2.5 inches long. So this is small enough to go into an MWD tool or a drilling tool, things like that. And it's enough processing power. And it's interesting because this is the minimum requirement for an aircraft is 32 bits. The other thing, and I've been working with these people for well over 10 years because that's kind of how long it takes to mature a technology. This is pretty mature. This is a brand new battery, operates at high temperatures. What we love about it is it's safe. It has no liquid components, so it's all solid state. So its room temperature performance is degraded. It does work at room temperatures, but its performance is relatively poor. But it's rechargeable, so this is just an example. I'm discharging it here. This is a single cell, 3-something volts. Discharged it here, and then I turned around and recharged it, and so this is current and voltage, you know, standard kind of thing. And it's 1.5 ohms at 225 degrees Celsius, which is quite a bit higher than lithium. But if you know anything about lithium, lithium doesn't do this. Secondly, lithium blows up in geothermal wells. They're quite dangerous. 500 degrees Celsius electronics. There's always discussion about 500 degrees C. This uses wide bandgap semiconductors. They're more than just silicon carbide, but just real quick. The technology is reasonably mature, but not anything near as mature as silicon. We really can't build complete tools out of it, or systems, unless they're extremely crude. But you do get to 500 degrees C. Right now, people are promising at least 1,000 hours of operation at 500 degrees C. It's nothing like you could use in an aircraft at 500 degrees C. Anyway, apparently some people in NASA actually said they ran some of them up to 1400 F and they were still working. I don't know what their resolution or capability was, but it's interesting. And they say, yeah, they don't have a voltage reference, which is something you really have to build a logic tool. So I'm asking the people in NASA to take this on as a project because we need it for our KMT project. We need a voltage reference. We could do a better voltage reference. We actually have one, but we need a better one. We could always use a better one. Let me put it that way. Okay, so here's the NASA Glen. I talked with them before I came down here. The idea is we want to involve these researchers not directly in the project because that's not how they're funded or what their objectives are. But their funding and objectives are close to what we need, so let's try to bring them in. One of them is Phil Nudek here, and they have a 600 degree C pressure transducer, but it's only rated 600 PSI. It's obviously a jet engine type of thing. We need something with a higher pressure rating, but it could be easily re-engineered for that. The Fraunhofer, their E-Harsh program, these are great guys, been working with them for years. They also are looking at 500 degrees C. What I like about them, they're looking at, oh, that's a typo. I know, anyway, that's supposed to be MEMS. Pressure and temperature for these kind of temperatures, and that's why they're doing that. And what's really kind of important, I think, is a MEMS 300 degree accelerometer. Here's a contact for there. There's also, we have some people here from the UK, and that would be Carl, I can't think of his name at the moment, I apologize. Anyway, Colin Johnston, that's his name. Colin Johnston, I can get his contact information if anybody wants to, and what they're involved in. Did I just go the right direction? Okay, real quick, I don't want to take up any more time. This is basically a cartoon proposal of sort of an initial concept for monitoring the magma. And this part would be in the magma. We would have tubing here. And then here would be the electronics, and we maybe have some mechanism to help us protect us from the actual magma temperatures and stay up here at a cooler temperature, and then transmit the information back up, basically using the instrumentation amplifier, because it could amplify the signal from thermocouples, which would be down here. So we've looked at modeling a little bit of how long that cable could be, things like that. All right, with that, we've come to my conclusion. The high temperature electronic solution up to 275 is pretty reasonable. The 500 degree stuff is still coming down the road, and high temperature batteries could enable Deward supercritical tools. With that, I'm done. Thank you very much, or Tuck, and I'll be heading to Paris.
Thank you for an excellent talk. One quick question from the audience?
Okay, goodbye.
I guess it was very quick. Thank you very much. So then we come to the last presentation of this session here, and that's by Mr. Árni Ragnarsson. see. And that is following maybe on one of the keynote presentations of this morning, I guess, by Ingólfur Þorbjörnsson. And it's on the GeoWell project. So please, Arni.
Good afternoon. I will give you a short overview of GeoWell, which is one of the ongoing geothermal projects funded by the EU Horizon 2020 program. The program or the project GeoWell is coordinated by ESOR. It's a 3-year project, started in February 2016. So we have now only about 2.5 months left of the project period. We have a strong consortium, 8 partners from 5 different countries, representing both the geothermal industry and the oil and gas industry as well. In addition to that, we have 2 third parties participating in the project. GeoWell is not about drilling. It's about design, completion, and operation, or I should maybe say monitoring, of geothermal wells. The main topics that we are working on are listed here. First of all, it is about the cementing of casing. That's one of the main components that we are working on. Also, our part is about the casings made of other materials, not conventional steel, but composite materials. We are working on flexible couplings that we heard about this morning in the talk of Ingólfur Þorbjörnsson. And material selection as well, both material selection for the casings and also for surface equipment. One more component is well monitoring. It's about fiber optic technique used to monitor wells, both during cementing and during the operation of the well. And finally, risk assessment of geothermal well, which is, I think, a relatively new or at least not widely used or applied in the geothermal industry. And these, what we are aiming at is, we have both conventional geothermal wells, high temperature wells, but also temperature at a higher temperature than conventional wells, 400, 500, even 550 degrees centigrade. And what I will do is, I might disappoint those who expect to hear much about the results, because I just need to refer to the reports produced in the project or deliverables about the results. But what I will do is just go quickly through all these components and give you a brief overview of what we are doing on these different topics. To start with the cement, the main work is done by TNO in the Netherlands with help, of course, from other partners. They started with doing analysis of the cement from the cement samples from the IDTB-1 well in Iceland. And actually, their results was that the cement that had been exposed to high temperature for a long time, they behaved very well, was in good condition actually. Numerical modeling has also been done related to this activity. TNO has also been working on creating different cement samples and testing them at high temperatures, up to 450 degrees, and tested the mechanical properties in laboratories. and also numerical geochemical modeling on the cement in general. Different type of cement has been done within this activity. I should maybe mention that in general, what we do in GeoWell is mainly work that is done in laboratory. Testing of material or properties or materials is mainly done in laboratories, but also partly a little bit in real geothermal environment. One part of this cement package is to look at the possibility or need for a ductile layer between casing and cement, because as we heard this morning, part of this is development of a flexible coupling that allows movement of the casing within the cement. And then there is a question about friction between the cement and the casing, and if it is easy for the casing to move or not. So that's why they are looking at the possibility for putting some kind of layer between the casing and cement to make it easier for the casing to move within the cement. This has been done doing both the testing in laboratories and also numerical modeling of this idea. And a little bit about further studies that have been done regarding the cement. Studies on the water content has been done, and the preliminary results shows that the water, not only water pockets, but also water in the cement actually can create relatively high pressures, probably too high pressures in the cement after curing. And the question is it possible to reduce this pressure and do something about it? And several options have been considered regarding this. And the last point regarding cementing is numerical simulations that have been done, computers on reverse cementing. Composite casings, I can go quickly through that because we heard all about it this morning in the talk that Ingólfur gave. No, sorry, we are not there. Sorry, composite casings. I forgot that. That is an activity done by a small company in the Netherlands that has been producing casings of composite material or glass fiber reinforced polymers for cold water. And the idea was to develop this further for higher temperatures. And originally the idea was to do it up to 140, 170 degrees centigrade. Unfortunately, the company that was working on this went bankrupt a few months ago, but a new company has taken over, so the activity is still ongoing. But it is clear that they will not manage to develop this kind of casings for that high temperatures, but hopefully somewhat higher than the existing production. Then we come to flexible couplings that Ingólfur talked about this morning, and I don't think I need to add much to that. He showed this diagram as well. As he talked about, it is because we know that the thermal expansion of the casing and contraction again when it's cooled down has caused a lot of damage in existing geothermal wells. So the idea is to produce case couplings that can take up this movement, as he explained. So, yeah, this is also just further on this topic, and some kind of demonstration of how the coupling is, or the casing is expected to move within the coupling. And the third one here, as he mentioned, I think the casings A prototype has been tested both in Norway, both at Sintef in Trondheim, and also Iris in Stavanger. And sliding function and mechanical properties strength has been tested at ambient temperatures. But the expansion has been just simulated by forces on the casing. So just to go to the next topic, material properties, the studies that have been done on that. TNO in the Netherlands has been doing or testing the optional or potential materials, so those who are listed here, at higher temperatures than we had information about before. Commonly, as I understand, the material properties or how they are, the strength is reduced by temperature. Commonly, the information commonly exists up to maybe 350 degrees, but in these tests they tested the material up to 550 degrees. So they are actually adding to this already existing curves, which is very important, of course, for the very high temperatures wells that we are talking about. Also, another kind of material test is tests that have been done here in Iceland at Reykjavik, just finished, that ESOR was responsible for at Reykjavik. That was not the mechanical properties, but mainly corrosion testing of different materials, both different types of steel and also cladded materials, in an autoclave that was operated at a well at Reykjavik, where actual steam from one of the wells was used in the autoclave, actually both in a container close to the well at the wellhead pressure and temperature, about 200 degrees and 20 bar, and also in the autoclave, where the geothermal steam was heated up to 450 degrees. And this was run for about 3 weeks, and samples have just been sent to Norway, Statoil or Equinor, that is going to analyze these samples. Then we come to the next topic within the geothermal, which is monitoring of geothermal wells. This is a technology which is maybe not quite new, but it has been under development for some time, and further development has been done within GeoWell. It is, as was mentioned, I think, this morning, a fiber optic cable was installed in IDTP2 well, down to about 800 meters. It is GFZ in Germany that is responsible for this activity, and the well was installed there in September. No, the fiber optic cable was installed in this well in September 2016, and when the casing was cemented. Actually, it is installed along the production casing, actually. And then measurements were done when they stopped injecting cold water in the well in September. So what they are trying to do is to pick up all changes, some changes in the operation, and do measurements of the temperature and strain by this fiber optic cable when something is changing in the well. And this is something that will then be within the wells if it will be used in the future. So you can always monitor the well during the lifetime of the well, actually. And the last item that I'm going to mention is risk assessment. It's actually not very common, as I understand, in geothermal so far, but it is a very important topic in the oil and gas industry. And the idea here is to use the experience from the oil and gas industry and somehow transfer it to the geothermal industry. It is Iris in Stavanger that is responsible for this, and they have done a lot of work, produced some papers and reports on this, made a survey within people both in the geothermal and oil and gas industry, and produced some kind of European protocol or recommendations for what we could do in the geothermal industry. And now the final part of their work is to use this protocol or demonstrate it on the activity that has been done in other work packets within GeoWell. For example, the work that has been done on cementing and flexible coupling and so on. And this was actually just, this describes what they have been doing, started with the survey, and are now doing some what they call reliability analysis on the other activities within the project. So this concludes my presentation.